Thank you for the introduction, Adam. Hi, everyone. So today I'll talk about our work on predicting impending exposure to malicious content from user behavior. This is joint work with my advisor, Nicholas, and our collaborators from KDDI Research. So if we think about it, traditional defenses are reactive in nature. They react at the time of security incidents or slightly thereafter. So for example, blacklists are used to prevent or deter users from visiting malicious websites at the time of the visit, while antiviruses react to stop malware at the time of download or execution. By the time these defenses react, it might be too late, as blacklists and antiviruses are usually the last line of defense. To address this, there has been some work on proactive defenses. However, such techniques were only shown to be practical over the long horizons. So for example, Canale et al. Proposed to predict whether users will be exposed to malicious content within a given period of 3 months. And they did so by using the user's behavior from earlier months. As another example, Soska and Kristen proposed to predict whether websites will be compromised within a given period of 1 year based on things like the content of the website or their structure. For this line of work, since there's a long period in which the security incidents can happen, we are limited in the set of interventions that can be performed. So for example, we might consider warning users about future exposures, but without knowing the actual context in which the exposure will take place, the warnings may not be very effective. In this work, our goal is to predict exposure to malicious web pages shortly before these exposures take place. So for example, you can think about milliseconds, 5 seconds, or 30 seconds before. We also want to do so using network traffic and not via intrusive collection on the user's machines. So to give you an intuition for why this is conceptually possible, imagine that there's this guy, John. And John usually browses news and technology websites. These websites are usually popular. And on average, John downloads and uploads about 3 megabytes per session. These patterns are normal and benign. But today, John really wants to watch the World Cup final. So we can see him going to visit streaming websites, and he's being served lots of ads. These websites are mostly unpopular, and John's downloading and uploading excessive amounts of data, about 30 megabytes in 1 minute. By the end of the session, John gets exposed to a malicious web page. And this raises the question of whether there was a way to proactively protect John. And one can expect that the browsing patterns should have raised suspicion. And this is mainly because of what we might know about other users who exhibited similar patterns and got exposed, and what we also know about how streaming websites often direct users to malicious content. The main benefit of short-term within-session prediction is that it can enable a variety of interventions to protect users like John. And these interventions vary from less aggressive to more aggressive ones. So on the less aggressive side, for example, we can consider alerting users about potential exposure, or we could prioritize traffic for additional inspection, which could potentially be expensive. On the more aggressive side, we could block the download of third-party apps, which could be dangerous. Or if we really care about the security of the network, so for example, if we're talking about a military network, we could terminate the connections completely. And to develop and evaluate our approach, we relied on 3 different datasets. The first dataset was provided by our collaborators from KDDI, a large Japanese cellular provider. This dataset contains HTTP requests made by 20,645 users, and these requests are text only. So for example, scripts and media requests are not collected. For each request, we have a consistent user ID, a timestamp denoting the time the request was made, a URL, and the number of bytes downloaded and uploading, among other things. This dataset spans 3 months, from April to June 2017, and the dataset was collected and used securely and with the user's consent. So in fact, to access the data, our collaborators had to commute to a secure facility because the dataset was not accessible via the internet. In addition to that data, we asked the 20,645 customers a bunch of security questions using an online survey. And specifically, we asked whether these users had prior security incidents, like whether they had account breaches. We asked whether they run antiviruses on their devices. We asked what type of marketplaces do they use. Do they use official or unofficial ones? We also asked them whether they would proceed on browser warnings. And we asked standard security behavior questions taken from the security behavior intention scale. And last, we asked a few questions to assess these users' confidence and their security knowledge. And the last data set we used was the Google Safe Browsing List, or GSB for short. This is a widely deployed blacklist used by the major browsers. A GSB can be used to tell whether a web page is malicious or not by querying its URL against a list. And since GSB is dynamic, we collected daily snapshots of it to detect when the users accessed malicious pages. So we processed our data into, or our HTTP data into units that we reason about. We call these sessions. And the session is a contiguous set of requests that's made by the same user, which ends when the user is idle for more than 20 minutes. Now we picked 20 as a threshold to be consistent with prior work on Sybil detection from clickstreams, but our preliminary analysis showed that varying this threshold did not affect the result much. So to give you an example, if you have a user who makes a set of HTTP requests, then she's idle for 40 minutes, then she makes another set of requests, then she's idle for 15 minutes, then she makes another set of requests, then the first set of requests would constitute one session, and the last two sets of requests combined would constitute another session because there is only 15 minutes between them. Given this definition of a session, the goal of our work can be formulated as predicting whether a user will be exposed to a malicious page later in the session by observing their behavior early in the session. So next, I'll talk about the window of exposure and behavioral differences between exposed and unexposed users. And the results of this analysis will serve as the bedrock for the last and main part, which is the short-term prediction. So after splitting our data into sessions, we found that exposure rate is not high. In fact, users get exposed to malicious pages only in about 1 per 1,000 sessions. Nevertheless, a high fraction of users get exposed to malicious pages. About 11% of users in our data were exposed to pages that were on GSB at the time of the visit, although these users are likely to be using browsers which use GSB. And this shows that the blacklisting approach used by the major browsers may not be sufficient on its own to prevent exposure. And even worse, we found that GSB might be lagging. More specifically, we found that visits to malicious web pages increase days before these pages appear on GSB. So in this graph, the y-axis shows the number of accesses to web pages, and the x-axis shows the relative number of days of visits from the page's appearance on GSB. So a negative number means that the page was visited before it appeared on GSB, while a positive number means that the page was visited after it appeared on GSB. What we can see immediately is that GSB is effective. After pages appear on GSB, the number of accesses to pages decrease. Unfortunately, however, there's a dramatic increase to visits to malicious web pages about 2 days before the first observation on GSB. Now, this increase is likely what triggers the detection of these pages as malicious in the first place, but it also means that there's a window of time in which the users get exposed, and we should try to prevent these exposures. And to capture this spike, we consider a web page to be malicious if it appears on GSB at the time of the visit or within 2 days after the visit. Now I'll present a few behavioral differences out of few that we found between exposed and unexposed users. And the first difference that I will show is that exposed users browse the internet more than unexposed users. Here, on the x-axis, we show the average session length in seconds, and on the y-axis, we show the empirical cumulative distribution function over users. A lower curve means that the group engages in longer sessions. And here we can see that the exposed users engage in longer sessions. And these differences are statistically significant. So for example, the median unexposed user browses the internet for about 250 seconds on average per session, while the median exposed user browses the internet for about 400 seconds on average per session. All right. As another behavioral difference, we found that exposed users request pages of certain topics at different rates than unexposed users. So for example, they request more ads. Here again, we show the CDF on the y-axis, and we show the fraction of ad pages requested out of all pages on the x-axis. And you can see that exposed users request add pages more often. So for example, add pages constitute about 26% of the pages requested by the median exposed user, while constituting only 21% of the pages requested by the unexposed user. In hindsight, this makes sense, right? As the more ads you request, the more likely you'll end up with a dodgy advertiser. It also means that more ads are also indicative of more aggressive monetization that could possibly be through sending users to malicious pages. And the last behavioral differences that I will talk about today is that exposed users browse the internet more frequently at night and outside of working hours. And here, the y-axis shows the number of requests, and the x-axis shows the hour of the day. And you can see, for example, that exposed users are more active between 3 p.m. and midnight. We also explored how exposed and unexposed users answered our survey. And to do that, we used logistic regression. In this logistic regression, the dependent variable was whether the users got exposed. So it was an indicative dependent variable. And the independent variables were derived from the survey responses that I showed you earlier. And interesting results from the model are that men are about 2 times more likely than women to get exposed to malicious content, and that users who have antiviruses are about 2.5 times more likely than users who don't have antiviruses to get exposed. And understanding the direction of causality here is tricky and requires more study. So it's possible that these users have a false sense of security and so they engage in more risky behavior, or it's possible that these users got exposed to malware in the past and so they installed antivirus. With these results in mind, it's also important to note that the model explains only 5% of the variance in the data. So this means that the self-reported data that we collected may not be sufficient on its own to explain exposure. And based on the behavioral differences between exposed and unexposed users, we derived features to use for predicting exposure. And the first type of features is what we call the contextual features. These are updated during the session after each request is made. And they include information such as the number of requests, the session's length in seconds, the distribution of topics within the session, and the time of day or week or time of the week in which the session took place, among other features. The second type of features that we use are the past behavior features. These are updated after a session ends, and they include information such as the average number of requests per session, the average session length in seconds, whether the users had past exposure, and more. And last are the self-reported features, which were collected via the survey that I showed you before. They include information such as whether the users on antivirus, whether they had prior security incidents, and more. And using those features that we developed, we train neural network to predict exposure after each request. And we mark a session as exposed if the neural network predicts exposure after any request in the session. So for example, if you have a user who visits Reddit, then goes to a streaming website and ends up in a malicious website, then we expect the neural network perhaps to predict that the user will not be exposed after visiting Reddit, but once the user visits a streaming website, we might expect it to predict that this user will get exposed. And we evaluated this approach using 5 20-day periods, in which the first 15 days were used for training and the last 5 days were used for testing. And we found that accurate within-session exposure prediction is possible. So more concretely, for different thresholds for discriminating between exposed and unexposed sessions, we computed the true positive rates and the false positive rates, where the true positive rates indicate the fraction of exposed sessions that were predicted as exposed, whereas the false positive rates indicate the fraction of unexposed sessions that were erroneously predicted as exposed. Here, we show the true positive rate on the y-axis and the false positive rate on the x-axis. And when predicting exposure up to 30 seconds before it occurs, we found that the system can achieve at least 74% true positive rate at 20% false positive rate. And if we desire to have less false alarms, then the system can be tuned to achieve 56% true positive rate at 3% false positive rate, for example. While this performance may not look very impressive, please keep in mind that we're trying to predict the future. And I'll also revisit this performance in a couple of slides and show you that actually, the system may be doing much better than I'm showing here. Next, we evaluated the importance of each feature type for predictions. And we did so by computing the performance of the system when using different subsets of features. And we found that the contextual features on their own are sufficient for accurate exposure prediction. So here again, we show the false positive rate on the x-axis and the true positive rates on the y-axis. And you can see that with the contextual features alone, we can achieve comparable performance as when we're using other features. And this is particularly exciting because the contextual features can be cheaply collected passively during the browsing session without storing any past behavior or past data and without asking users any survey questions. So all of this doesn't mean that we're done yet. If you remember from earlier in the talk, the exposure rate is low. There are about 1,000 unexposed sessions per exposed session. And as a result, there is a high chance of false alarms. So for example, at the 56% true positive rate and 3% false positive rate operating point, the system achieves about 56 true detections and about 3,000 false detections per 100,000 sessions. So does this mean that the system is not useful? Fortunately, it turns out that this isn't the case. We found evidence that most false alarms may actually be true detections. I did so by checking against VirusTotal, a widely used service that brings together information from multiple blacklists that are typically more inclusive than Google Safe Browsing. What we found is that the exposure rate may actually be 24 exposed sessions per 976 unexposed sessions, and that the operating point in which the true positive rate is 56% and the false positive rate is 3% may actually correspond to true positive rate of 96% and false positive rate of 1%. And under this more inclusive ground truth and operating point, the system actually detects or achieves about 2,200 true detections and about 870 false detections per 100,000 sessions. And this performance is much more practical. So to wrap up, we propose short-term prediction to enable proactive defenses. We explored the behavioral differences between exposed and unexposed users to devise useful features for these predictions. And we showed that short-term prediction can be done relatively accurately. Thank you.
Hi. So it's a common belief that visiting sites with adult content is a place where you get exposed to malware more often. And I noticed that there's some of the correlations you point out, such as browsing in the evening and stuff like that, also correlates with that. Do you think that adult content would be a useful feature to incorporate it into your predictor?
That's a great point. And I had a slide showing the differences between how often exposed users and unexposed users browse adult content, but I removed that slide for the purpose of this talk. And we showed that, yeah, we found that they browse, like exposed users tend to browse adult content much more often. And that was actually part of the features that we used. So we had like for 99 categories, how often or what's the distribution or what's the fraction of time in which the users spent at these websites.
Thank you very much for the work. I like it a lot. I have a couple of questions about the data. Can you talk a little bit about the process that you used to acquire consent on that? And then if I remember right, this is a data set from Japan. Do you have any sense of how unique it is to Japan?
So about acquiring consent, the company by itself, when the customers come, they ask them to opt in for data collection in return to certain benefits. And on top of that, we also, when administering the survey, we asked people if they would approve using their data for this specific research project. And so I think we sent this survey to 600,000 customers, and out of them we had this about 20,000 that responded and approved. As for the differences between what we see in this data and what's in like how much it generalizes to different populations. I think that we need to just study it to find out. So probably the approach will be just the same, and we'll need to run it. We cannot do this without further studies. Yeah.
Go first, Nick. Thank you. You seem to be able to tell when something was added to the Google Safe Browsing list. Can you tell us how you do that?
So we collected daily snapshots of it, in the sense that every day we would download all the full hashes from the database, and then we would test the URLs in our database.
Right, but the way that's implemented, essentially, you have hash collisions in which you have to ask the server, right? So it seems that it's not possible to do this historically unless you have help from Google.
So you would have that if you have the small hashes. There are two types of hashes. And then for the full hashes, you should be able to do this.
So you don't need to do extra queries for the full hashes.
Yeah.
Okay, thank you.
Hi, Ben Schock from CISPA. Very interesting work, thanks. Two questions. One is about the features that you're using, the contextual features. Did you check whether you need all of them, or you can kind of go with a smaller set? That is the first question.
Yeah.
And once you answer that, I have the second stabbing in the back question. No.
Yeah, so we did not look at, like, we tested the effect of different features at the high level that I showed here. We compared the server responses with the past behavior and the contextual features. It would be nice to get do a more granular analysis and see how the different contextual features would compare to each other.
Okay.
But we did not do that.
And the follow-up question to this is HTTPS. So what about that? Then topic, you can, for some IP addresses, you can guess maybe. Maybe you can use SNI to determine certain host names, but not in all cases, right? So what about this? I'm assuming that you're looking at HTTP traffic, not HTTPS traffic. How would that system work if you have what we hopefully have soon is like HTTPS everywhere?
Yeah. So it'd be nice to test it, but I imagine that the bulk of the main part in which we use the entire URL is when we run the topic assignment, right? And perhaps in HTTPS, in cases where you have only the domain name, you could just use the domain name and see how much this would generalize and work in that situation.
Yeah. All right. Thank you.
Yeah.
Hi. You used, I think, 15 minutes, if I remember correctly, as the session boundary time. How did you come up with 15 minutes?
So we used 20 minutes, and that was the user had to be idle for 20 minutes for the session to end. And we picked this simply to be consistent with prior work on Sybil detection from clickstreams. Yeah, but our analysis showed that varying this slightly did not really affect the result by much.
Any other questions for our speaker? All right.